Hi, and welcome back to ScottiesTech.Info. I'm Scotty, my co-host Cletus, and this is episode number 5 of EEK, the electrical engineering class. And Cletus just committed suicide. Oh, no, he's alive. Don't, yeah, okay, there you go. So, right, EEK, episode number 5. In the last episode, I covered three-phase power. So far we have current and voltage and power and all that kind of stuff, and power generation, three-phase power. So of course now the power has gotten to your house. So this video is about the basics of a circuit breaker panel. And the reason I'm doing this video is because I've seen many times that people sort of like, a breaker trips and they open the panel and they kind of look at it like, and then they like call an electrician or something. So I just wanted to kind of go over the basics of a circuit breaker panel, because actually it's basically just a bunch of light switches. It's very simple. So let's take a peek. Right, so these are some circuit breakers here. We'll get to that in a minute. But basically, when power comes into your house, what you have is a main breaker. So this is that's your main breaker. And then inside your house you have your circuit breaker panel, which is usually several rows. Just a note, by the way, this is actually kind of how breaker panels are done in most of the world. Sometimes in the US and North America, the panels are vertical, and that's a little different because they're split phase. So this is kind of everything I'm about to say applies to breaker panels no matter where you live in the world, but it might look a little different. So just keep that in mind. These are actually they're basically European breakers for 230 volts, but like I said, the actual functionality of these breakers is exactly the same pretty much everywhere in the world. So, right, so here's your main breaker, and here is your breaker panel in your house, right? So these guys are connected. We'll just do kind of single phase, right? So you've got your live, you have your live and your neutral coming in from your power company, and then you have your neutral going to this guy, and your neutral going to this guy. That's beautiful. And then you have your live going to this guy, and your live going to this guy. And then the output of this guy actually goes around behind, and he powers all of these breakers, both. So basically, power comes into here, and this guy, this fat one, powers this entire row of normal circuit breakers. So that's basically how it's wired. Oh dear, I just got blue ink all over my finger. Right, so each of these fat guys, these are your two different types of breakers, right? So this guy is I call it a differential breaker. It's also known as, in France anyway, it's called literally a differential breaker. You'll see why in a minute. This is also known as an RCD, residual current device, and also a GFCI, a ground fault circuit interrupter, and there's all kinds of different names, but we'll call it a differential breaker. This is your fat guy right here, and each one of these protects several of these regular circuit breakers. So what exactly is a differential breaker? Basically, this guy he's detecting, he has a rating on him, say like 63 amps, right? That's much higher because you see like this breaker, this is a 16 amp circuit breaker. Well, what the heck? Differential breakers protect against leakage currents. They don't protect against overcurrent conditions. But essentially, it's just a light switch with protection. That's on, that's off. So when you turn this differential breaker on or off, it cuts power to this entire row. And when you turn this differential breaker on or off, it cuts power to this entire row. The rest of each of these rows, of course, being normal circuit breakers. So the differential breaker, I like to call it a differential breaker because inside one, it's very, very, well, okay, it's not simple, but the general idea is that inside there's kind of like this toroid, and basically you have your, this is not what they actually look like, I'm just drawing it for simplicity. You have your neutral wire wrapped around and your live wire wrapped around. And, oh look, I just marked him up. I'm doing pretty good today. The whole idea here is that when you have, say, this is of course alternating current, right? You've got your live and your neutral. So the current's going to go in this direction, then this direction, then this direction, and it's going to change direction 100 times a second at 50 hertz or 120 times a second at 60 hertz. So let's say you have 1 amp going in, right? That means you have 1 amp going out here. That also means you have 1 amp coming back out. A device operates at a certain voltage, say 230 volts, and it draws a certain amount of power, say 1 amp. And then we say, of course, power equals voltage times current, so power equals 230 volts times 1 amp, that's 230 watts. But current is not actually consumed. So you're operating your gizmo at a certain voltage. If you've got 1 amp going this way through this differential breaker and into your gizmo or your power outlet or whatever, the same amount of current is coming back. Even if your gizmo is, say, a fan and it's consuming, it's using power and it's performing some kind of work like rotating a fan or something. The current going in is always going to be the same as the current going out, unless there's a fault condition. So let's say you have your gizmo and you've got your live and your neutral going in, right? But there's some kind of fault condition where suddenly some kind of fault occurs where, let's say your live or say your neutral there's a fault and somehow it gets connected to the chassis, right? And of course the chassis is connected to earth ground. What that means is that you might have, say, 1 amp of current going in here, right? But some current is actually leaking to ground. So your current coming out of here, these aren't going to be equal. So say, here we might say that, like, where's my eraser? There it is. Instead of, I drew everything backwards. Well, it doesn't matter, it's alternating current. So let's say, gotta erase that one too. Instead of 1 amp going in, there's a fault condition, so only 0.9 amps are coming out, right? That's what this guy detects, because when the current's going through this little toroid thing, this is basically like coils of wire on like a toroid, blah, blah, blah. When the currents are equal, and this guy is on, he'll stay on. But when there's a difference, when there's a differential in the current, i.e. some current is leaking to ground, or maybe you touch one of the wires and you are the path to ground, like through your arm and hopefully not through your heart and through your foot into the ground, or you're touching something and this part of your arm touches a grounded surface or something. That's a leakage current, which means the current going in and the current going out will not be equal. And that, because this is a magnetic gizmo, the magnetic field this generates becomes unbalanced because current going in is not equal to current going out, and that means this guy will go book and he'll trip. So that is a differential breaker / GFCI / RCD, and the rating on here, the current rating, is the maximum amount of current that this guy can handle. So each one of these protects a whole row of normal breakers. This guy can handle 63 amps total current before he melts or fails or whatever, right? And then it says, okay, your voltage is 240 volts, and it says 30 milliamps. 30 milliamps is actually the difference, the current differential that this guy will tolerate when he's on. When he detects 30 milliamps of leakage current or more, he trips. And that basically protects against various types of device gizmo failures, and also it's primarily for electrocution prevention, because like I said, if you touch a circuit or you touch your gizmo that's plugged in and there's a fault, when 30 mils or more of current starts to flow through you, this guy will trip. And that's all very complicated, why they pick 30 mils, blah, blah, blah. The average person in average health, average age, blah, 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 if this guy trips at 30 mils, then you will not, it will hurt like hell, but you won't die. That's the whole point. These are to protect against, primarily against electrocution. Okay, so that's a differential breaker / RCD / GFCI. And those are in our row here. As I said, each one of these protects a whole row of these guys. Now these guys are, typically, it's a normal circuit breaker. It's on, it's off. Again, it's a light switch, but it has a purpose. It offers protection. In this case, it says C16, which means this is a 16 amp breaker. Now, at 230 volts. These guys actually, this is actually a, typically they're thermal magnetic circuit breakers. And what that means is that this guy inside here, he has usually like a coil. And if there's a very high current that goes through, that coil is energized and it pulls a little latch and this guy goes and turns off. It also has the thermal aspect of, that's the magnetic aspect of the protection. Very large current goes in, trips the mechanism, flips it off. The second part is usually a little, a bimetallic strip, which if you, I'll put a link in the description and you can watch my video on how does an electric tea kettle turn off, because that explains bimetallic strips. The same thing is used in here, and the bimetallic strip part is the thermal part, and what that's for is basically when you get, say this is rated at 16 amps, when you get, say, 14 amps is flowing and then 15 amps is flowing, that bimetallic strip, like, he starts to heat up, and right when you hit about 16 amps or maybe slightly less or maybe slightly more, the bimetallic strip goes buck and bends enough, which also takes your breaker and goes whoosh and flips him off. So these are typical generic circuit breaker, which are usually thermal magnetic breakers, and they are for overcurrent conditions. They don't protect against electrocution, blah, blah, blah. They also protect against, if you have your live and your neutral at the output and you short the wires together, obviously you'll have a very large current flow, and usually the magnetic portion would kick in because it'd be a really big current and he'll flip off. So essentially you have these two types of breakers, which each are basically a fancy light switch. And this guy protects against mostly electrocution. He detects the 30 mils of leakage current to protect against electrocution, as well as certain device faults. Like sometimes you have a washing machine or something, and there's leakage current, and it's a minor fault, but this guy detects it and he'll trip because there should not be lots of leakage current normally. And then each one of these protects a whole row of normal thermomagnetic breakers, and the purpose of these guys is strictly to detect overcurrent conditions, because there's also 20 amp breakers, 16 amp, 20 amp, and typically like a 16 amp breaker will be associated with a certain diameter of wiring coming out of it, and a 20 amp breaker will be usually fatter, thicker wiring coming out, and you have to use a specific size of wire with a different type of breaker, and depending on where you live, there's certain rules and regulations. Like if you have a 16 amp breaker, you use such and such gauge wire, and you can only hook up X number of power outlets to it. Whereas if you have a 20 amp breaker, then you have to use this diameter of wire, and you can hook up more power outlets to it. Those rules you have to actually check depending on the country where you live. They're different for every country, and yeah, it gets complicated. But so that's pretty much it. That's what a circuit breaker panel is. So one last thing to note here, so you have your main breaker here. This guy actually serves two purposes, and he is actually, like, say you have a 100 amp hookup. This main breaker here that your electrical company installs, say he's a 100 amp, you have 100 amp service. This main breaker is actually a 100 amp thermomagnetic circuit breaker, more or less, but he's also, and this value varies depending on where you live and stuff, he's, say, a 500 mil differential breaker. Okay, but why is that? The reason for that is because usually they do it this way because your main breaker, if it detects 100 amps of current, obviously if you have a 100 amp sort of subscription to your power company, you can't suck more than 100 amps, right? So your main breaker at 100 amps, he's going to shut off because the power company doesn't let you pull more current than you're subscribed for, right? But he also has this, usually, sometimes it's 300, where I live it's 500 milliamps, 500 mil differential detection, which is obviously much higher than 30 mil. And the reason for that is usually fire prevention. So if there's 500 mils or more of leakage current, this guy's going to trip. But there's a little catch, because when you have these dudes, this is a differential breaker, and each of these is a differential breaker, right? So say you have a very large leakage current, say 600 mils. This one will trip because 600 is greater than 30, and this one will trip because it's 500. So which one is going to trip first? Well, what they do is, this is usually a selective. Usually on the box they'll have at least where I live, they put an S on it, and that means it's selective. And all that means is that this guy is going to trip. It's something like 200 milliseconds, whereas this guy, also a differential breaker, he's going to trip in, as it says written on here, you can maybe see that there, he says 0.1 seconds, 100 milliseconds. So the whole idea here is that this guy has a delayed trip. So that allows the differential breakers here to trip first, and then second, this guy will trip. That's just a little technical detail. Right, so that's pretty much it. If you have a breaker tripping, actually I think I'm going to make another short little video about that, because that's another thing I've seen that people kind of have no idea what to do if they have a tripping breaker, and like, what do you do? Most people end up calling an electrician, so I might do that for my next video. But yeah, that's pretty much it. Like, that's your circuit breaker panel. You've got a differential breaker, and each differential breaker protects these normal circuit breakers all in the same row. If you turn this guy off, this whole row goes off. These guys, the differential breakers, they protect against mostly electrocution, leakage current, and all the rest of these normal circuit breakers, like these guys. Those are for overcurrent conditions, short circuit, sort of more like catastrophic, too much current is flowing types of failures. So that's it. It's just a bunch of on-off switches, and say, like, you know, this guy here, he might be connected to, say, like, your living room. Done. And that's it. So if you flip this guy off, you're cutting power to the power outlets, say, in your living room. If you flip this guy off, you're cutting power to this entire row. But all they are is essentially on-off switches. On, off. But they serve a different purpose than a normal light switch. So I think that's pretty much all I wanted to say. Like I said, I think I'll do another video about how to debug tripping breakers, because that's another thing I've seen that people are sort of mystified about. So, but that's pretty much it, and hopefully it sort of demystifies the breaker panel, so that next time you open it, you won't look at it and go like, "Oh my God, what is this?" Because it's really actually pretty simple. So, having said that, if you don't know what you're doing, don't ever open one up, because you'll electrocute yourself. So, right. So, for more techie tips, see ScottiesTech.Info. Thanks for watching. See you next time.